Hi everyone, this is EE311 or Electrical Machines 1, and in this course we will talk about DC machineries. So for this lesson, we will be dealing with direct current machinery fundamentals. What is an electrical machine? So when we speak of electrical machine, it pertains to a device that converts mechanical energy into electrical energy or vice versa. So the conversion can be from mechanical energy to electrical energy or from electrical energy to mechanical energy. Then electrical machines also includes these transformers, which do not actually make conversion between mechanical and electrical form, but rather they convert the voltage level from one voltage level into another voltage level. So for the classification of electrical machines are classified as static machines or dynamic machines. And under static machines, we have transformers, and for the dynamic machines, we have the generators and motors. So under generators, we have DC generator and we have AC generator. And under motors, we have DC motors, we have AC motors, and we have universal motors. So in this course, we will talk about DC generators and DC motors. Okay, so direct current machinery fundamentals. So for the generator action, an induced EMF or voltage or an EMF or voltage is induced in a conductor if it moves through a magnetic field. So the rotor of the generator moves through a magnetic field and it creates or it induces a voltage in a conductor. So for the motor action, a force is induced in a conductor that has a current going through it and placed in a magnetic field. Then for any DC machine, it can be either or it can act either as a generator or as a motor. So depending on the uh, purpose of the DC machine. So in this slide, we have here a picture which is a simplest rotating DC machine, and it consists of a single loop of wire rotating about a fixed axis. So the rotating part of the machine is called rotor, and the stationary part is called the stator. The magnetic field for the machine is supplied by magnetic north and south poles. So with uniform air gap, the reluctance is the same under the pole faces. So for the voltage induced in a single rotating loop, so if the rotor is rotated, there will be a voltage that will be induced in a wire loop. So the voltage on each segment is given by the formula E induced is equal to V times B times L, wherein our V is the speed of rotation of the loop and B is the magnetic field and L is the length of the conductor. So for the total induced voltage, we have 2 VBL. Okay, so in this equation, we have the V as the speed of rotation, and the capital letter B is the field in which the loop is rotating. So meaning this is the magnetic field, and L is the length of the conductor. For illustrative example, we have here a sample problem 1. A A piece of conductor 10 centimeter long moves across a magnetic field of 10,000 Gauss at a velocity of 120 centimeter per second. So what voltage appears across the conductor? So for the solution, so we will write first the given of the problem. So the L is equivalent to 10 cm. Then our magnetic field is equivalent to 10,000 Gauss, and our velocity is equal to 120 centimeter per second. But take note that L should have a unit of meter. So this 10 centimeter, we need to convert this into a unit of meter. So 10 centimeter is just equivalent to 0.1 meter. Then for Gauss, for the magnetic field, it should be converted into the unit of Tesla. So we have 1 Tesla is equivalent to 10,000 Gauss. And for the velocity, it should be in meter per second. So 120 centimeter per second is equivalent to 1.2 meter per second. And we will just multiply the three given of the problem. So our E induced is equivalent to VLB. So we have the velocity, which is 1.2 meter per second, times the length, which is 0.1 meter, times the magnetic field of 1 Tesla. So simplifying, we have E induced is equivalent to we have 0.12 volts, and that's the voltage that appears across the conductor. So in general, the voltage in any real machine will depend on the same three factors. So we have the three factors: the flux of the machine, the number two factor is the speed of rotation, and the number three factor is constant, representing the construction of the machine. Then how do we get the DC voltage out of the rotating loop? Because in the conductor, in the loop, the voltage produced is AC. So using the mechanism called commutator and brushes, we can produce or we can obtain DC voltage from the AC voltage. So at the instant when the voltage in a loop is zero, so the contact short circuit the two segments. So every time the voltage of the loop switches direction, so the contacts also switches direction, and this process of connection switching is called commutation. Then we have the induced torque in a rotating loop. So the force and the torque on the segment of the loop is given by these two formulas. We have for the force, we have ILB, or the current times the length of the loop times the magnetic field, and the torque is given by RF sine of theta. Then also in general, the torque in any real machine will depend on the same three factors also. We have the flux, the current, and the constant, representing the construction of the machine. Okay, for the DC machine construction, so the stator of the DC machine has poles. so which are excited by either DC current or permanent magnets. So the excitation may come from DC current in a DC machine or permanent magnets in order for the DC machine to produce a magnetic field. But more preferably, uh, the DC machine is excited by DC current rather than permanent magnets, because in permanent magnets you cannot adjust the magnetic field strength, while in if we have DC current in the coil, so we can adjust the strength of the magnetic field. Then in the neutral zone, in the middle between the poles, so we have commutating poles that are placed to reduce the sparking in the commutator. So in this uh, figure, we have here the main poles, and in between those poles we have the commutating poles, and the purpose of this is to reduce the sparking in the commutator. Then compensating windings are mounted on the main poles, and this reduces flux weakening commutation problems. So the poles are mounted on the iron core that provides the closed magnetic circuit. Then the rotor has a ring-shaped laminated iron core with slots. So then coil with several turns are placed in the slots. So the distance between the two legs of the coil is about 180 electrical degrees. Then the rotor coils are connected in series through commutator segments, and ends of each coil are connected to a commutator segment. So the commutator consists of insulated copper segments mounted on the insulated tube. Okay, so in this figure, or in this photo, you can see the rotor of the DC machine. So you have there the iron core and the coils inserted on the armature. Then we have the coil commutator interconnection, then insulation between segments. So we have also coil insulation there. So for the commutation process, so commutation is the process of converting AC voltage and currents in the rotor of the DC machine to DC voltage and currents at its terminal. So this process converts AC current and voltage into DC current and voltages in a DC machine. So that is called commutation. So for the problems with commutation in real machines, we have number one is the armature reaction. So what it does is that it weakens the main flux and distorts the main flux and neutral plan shift. Then the LDIDT voltage, so it occurs in a commutator segments being shorted out by the brushes. So the effects are arcing and sparking in the brushes. Then we have also flash over, so reduced brush life and pitting of the commutator segment. What are the solutions for the problems in commutation? So we have we have three lists here: shifting, commutating poles or interpoles, and compensating windings. So for the commutating poles or the interpoles, what it does is it cancels the voltage in the coil, so undergoing commutation. Then interpole windings are in series with the rotor windings. So as the rotor current increases, flux produced by the interpole also increases. So producing an opposing effect to that of neutral plunge shift. Then we have compensating winding. So solves the problem of flux, weakening, and neutral plane shift. So compensating windings are in series with the rotor windings, then placing in slots carved in the faces of the poles parallel to the rotor conductors. Then we have a power flow and losses in the DC machines. So listed here are the power losses which can occur in a DC machine, be it a DC generator or a DC motor. So we have number one is the electrical or what we call the copper losses. Then we have the brush loss or brush losses. We also have the core loss. We have the mechanical loss and stray load losses. So for the brush loss, the formula is the power in the or the brush loss is equal to V times IA. So what is V sub BD? So this is the brush contact drop or the brush drop. Then IA is the armature current. Then for the copper loss, we have the armature loss, which is equivalent to the square of the armature current times the armature resistance, and the field loss is equal to the square of the field current times the field resistance. So for core losses, it is divided into two, which is the hysteresis loss and the eddy current loss. So it occurs in the metal of the conductor. So these losses vary as b squared and for the rotor as n raised to 1.5. Then mechanical losses. So losses due to friction are caused by the friction of bearings in the machine. So we also have windage losses caused by the friction between the moving parts of the machine and the air inside the motor casing. Then for the stray losses, we have the unknown, it is the unknown loss. Then by convention, this is to be 1% of the full load. And for the power flow diagram, we have the power flow for the DC generator and the power flow for the DC motor. So for the DC generator, we have the mechanical input power. Then we have the mechanical loss. So mechanical loss, then core loss, then copper loss, and stray losses. Then we have the electrical output power. So for the power flow diagram of the motor, we have DC electrical input and field copper loss. Then papasok siya doon sa ating armature. So we have the armature power input. Then magkakaroon ng armature copper loss. Then the power developed in the armature. After that, we have the friction, windage, and stray losses, and eventually we will come out with the output power. So that is the power flow and losses in the DC machines. So that's it. That is the DC machinery fundamentals, and our next lesson we will talk about armature reaction. So thank you for watching this video, and I hope you learned something